Thank you very much. Is the sound working okay? So let me start by saying that this is joint work with Sungwoo, who, if you want to put your video on and wave, Sungwoo, everybody will be able to see you. Otherwise, everybody sees your picture. Oh, whoops. No, oh, it changes your position. So we have to do something about that. We got to go find you now. There you are. So if you want to wave, now everybody can see you. All right. Perfect. So it's just an amazing pleasure to be in a live conference audience. And I know I'm speaking for everybody. You know, when you're holed away with, in your COVID cave or whatever we call it, you could tell yourself that travel is a nuisance, the time in the airport's a waste, it's bad for the environment, all these things are true. But there's nothing like being in person, having you want to tell me that I have 5 academic grandchildren right here in the audience I didn't even know about. Reminiscing with Anne here about the last time I was giving a talk at UW and the water heater broke back home and it was a disaster. Or, having Percy tell me about how he started in random matrix theory. I mean, all of these things and the many other conversations that I've had, you just can't do that on Zoom. And so it's really a great pleasure and I'm very happy to be here. So this is a talk about structure. This is a talk about mathematical structure. I guess the mathematical stereotype is that structure is the domain of the pure mathematicians, I suppose, and the applied mathematicians kind of work on the special cases, maybe by some sort of stereotype, and the theoretical physicists want the grand unified theory, right? And so this is about that, and in particular, when we think about matrix factorizations, I don't think we usually associate that with big theories, right? We tend to think of them. I think the notion of a matrix factorization, you probably think back to an early linear algebra class where you did Gaussian elimination with paper and pencil, right? It's a very nuts and bolts kind of thing. And yet I'm going to try to convince you that matrix factorizations are very close to the bedrock of structure in mathematics, and how this, on the one hand, relates to random matrix ensembles, and I'll give a few of my must-know ideas in random matrix theory to complement Arnaud's. And also, this other paper is in numerical linear algebra, where we love to play with matrix factorizations. And so, inspired by the theme of the conference, I did put up these 2 papers, one squarely in the area of numerical linear algebra, and the other on random matrix theory. Okay, and one more shout out for Sungwoo. Just came back from the Householder meeting, and Sungwoo was an honorable mention for his PhD thesis for the Householder Prize. So that was great to see. Okay, so there's a lot that I'd like to do in a short amount of time. Okay, why is my computer stuck? There we go. Yeah, alrighty. So let me start off with a random matrix story that's about 60 years old. So many of you may be familiar with Freeman Dyson's early papers about the circular ensembles and the Gaussian ensembles and so forth. So in 1962, Dyson wrote a paper where he wanted to do like a grand unified theory of some sorts, right? He wanted to bring together unified ideas that were, in his, from his point of view, came up in the last 30 years. He wanted to put together the mathematics of group representations and Wiles' theory of algebra with random matrix theory, right? So like, how can these all be connected? I can only imagine that Dyson didn't like the idea of there being, this ensemble and that ensemble and the other ensemble. Like, he must have wanted a way to sort of connect them into the bedrock of mathematics, right? And it took him 8 years to mention that maybe somehow the mathematical notion of symmetric spaces should play a role in this. Okay? And then in many years that came by later, 96, 2004, various physicists and mathematicians tried to realize Dyson's dream. So I first learned about this from Martin Zirnbauer, who's gotten a lot of fame for connecting random matrix theories to symmetric spaces. Zirnbauer worked mostly on the non-compact spaces. There was Dueñez, who was a student of Peter Sarnak's, who worked on the compact spaces, and there are others connecting random matrix theory with Cartense KAK decomposition, which is a kind of a generalization of the SVD that goes back to Cartan. And here's how the idea goes, and I'll show this to you. You start with one of these nice little mathematical tables of symmetric spaces, a pretty small table really. And what you want to do is for each symmetric space, connect it with a random matrix theory. Okay? And I saw Zirnbauer do this around 1996 and didn't really know what a symmetric space was at the time and couldn't quite figure out how to connect them to a random matrix theory. And so I started a series of emails with Zirnbauer. It was very polite. I kept asking him questions. I kept prodding him, but couldn't rest. And it finally occurred to me that some of the Jacobi ensembles are missing. Right? And that just bothered me. It didn't seem to bother him. It's like, well, we got most of the ensembles. Like, he seemed okay with it. But it nagged at me for a long time that really mostly all of the Jacobi ensembles were missing. And it became clear that the symmetric space stream was kind of on the right track, but it was also too restrictive. It was almost as if folks tried too hard to make this symmetric space thing work. Okay, and with Sungwoo, we kind of have the completed theory. Basically, what has to happen is the symmetric space alone is not enough. It turns out that there are multiple coordinate systems on each symmetric space, like there is on any space. And the different coordinate systems lead to different random matrix theories. Okay, and so this leads to alternative matrix factorizations. And as I would like to say, matrix factorizations at the core of everything. Now, of course, I like numerical linear algebra, so of course I would say that, but that's what I feel. Okay, so now let me turn to another slide, which is kind of in the same vein, and talk about numerical linear algebra. Okay, so I saw this paper by the two Mackeys and Francois Dessert about which groups have almost structured SVDs. And by a structured SVD, we mean that somehow your matrix has some structure, like of some various kind, like maybe A is orthogonal or asymmetric or whatever. And we would like to know when would, say, U and sigma and V also have that same structure. Okay, and so we have a completed theory to this one, and this led to 53 matrix factorizations, most of which are new. Okay, and again, realizing that matrix factorizations, I mean, really matrix factorizations on one hand are just changes of variables, right? When you go A equals U sigma V transpose, you're expressing that same point in matrix space with another coordinate system, right? And so again, matrix factorizations at the core of everything. Okay. So here's the little banner that I assume Tom made so nicely, or at least put up on the web over there, the Conference on Random Matrix Theory and Numerical Linear Algebra. And I would like to talk about the interplay of these two areas. And I love it when pure mathematics has something to say about applied math, but I love it even more when it goes in the other direction. Okay, and here's a story. Joanna knows about the tridiagonal, the beta ensembles is one such example. But one doesn't usually think about things going in the other direction, but it can and it does. And here's one such story. And of course, the best way for areas to interact is to have scientific bilinguals. And I feel there are a lot of them in this audience. And so I probably would be preaching to the choir. But it's great to know more than one area to see these sorts of things happen. Okay, so as far as matrix factorizations at the core of everything, this isn't exactly lined up with the way I'm thinking, but it's probably no more than 20 degrees off, where Nick Jafethin and Alex Townsend would talk about the fact that in a way, it's a big deal that you have matrix algorithms and they're encoded into factorizations, right? That, before there was Gauss elimination and then there was LU, right? And so the factorization encodes the algorithm. Of course, if all you have is a hammer, maybe this is how we see the world. Okay, so so the structures that we need to talk about are so-called double coset structures, and we found them to be rich and comprehensive. Okay, and there's so I'll bring this up in a minute, but there's a whole lot of vocabulary, and I'm going to guess that many of you may know what one or two of these things are, but maybe not what all five. And this leads to me. This is a bit of a problem for me because I kind of wish you would know all five. right? But here's some vocabulary, the random matrix theory, Lie groups, symmetric spaces, Cartense decomposition, and the generalized singular value decomposition, okay? And I thought about, how do I do this? I could go through all 5, and then I would get to the results by the end of this talk. That would be the logical way to go, but it'd be sort of boring. So I decided to go the other way around. I'm going to tell you the results and then tell you what these things are. Okay, and this reminds me that I often tell students, I don't know if I told this to you, Joanna, or not, but Raj remembers my telling him that the best way to read a paper is from the middle. And some of the students say, that's crazy, you can't even understand what's going on, right? I mean, you have to start from the beginning or there's no logic to it. And that's true. I still say, read a paper from the middle, come up with a guess as to what it's about, and then go back and work your way through is the best way to read a paper. And well, that's kind of what I'm doing. So Percy just said, maybe I should start my talk in the middle. So let me, at the very least, put up 53 matrix factorizations. You're not going to be able to really read them, but I'll point out a few. And the ones that don't have a gray background are new matrix factorizations. So the gray backgrounds, I hope you could see them, are ones that we have found in the literature. And so, for example, over here on, well, let's start with F7 as the singular value decomposition. The first column are real matrices. The second is complex. The third is quaternion, which is kind of the favorite. The CS decomposition, which is related to the GSVD, is up there in F4. On the first row, there's this ODO decomposition, which is known, which says that a unitary matrix could be written as orthogonal, diagonal, unitary, and orthogonal. Many of these were discovered by numerical linear algebra people, some by physicists. Some of these factorizations have names that don't apply to the person who invented it, but that's not unusual in mathematics, and so forth. Okay, there are some of these are labeled in a brownish color. I hope you can see it, like F1 there and F7. Those are examples of Cartense KAK decomposition. I haven't told you what KAK is yet, but at least I'm going to tell you that the SVD is one of those things. Right? If you go to the Wikipedia article about Cartense decomposition, you'll see that it is a generalization of the SVD. The ODO is another KAK. In the case of the GSVD or the CS decomposition, it's partially brown because the KAK decomposition when you have sort of a square matrix in your decomposition, then it's a KAK, but when it's rectangular, it's not. All right, so we have lots of matrix factorizations, and many of these are new. I suppose about 40 of these are new. I suppose I could not have shown you this, and maybe we could have written 40 papers one at a time. One new matrix kept us busy, I suppose. But we decided not to do it that way. But in many of these, there are a lot of open problems, like stable algorithms for calculating these things. What are they good for? I mean, there are many questions that one can ask for these matrix factorizations. Okay, but let me move on over to this table with all these funny symbols that I suspect many of you may not know what they are. But whatever it is, it's a small table, right? So this is Carten's list of symmetric spaces. And I'll just tell you what some of these are. But I love nice little compact tables, right? I mean, it's like, you can put them in the palm of your hand, whatever they are, you feel like you can one by one figure them out. So let's see. So here are a few things. Let's see. Here's the unitary matrices. You know what those are. Here's the special orthogonal group. Those are the determinant 1 n by n matrices that are orthogonal. Let's see. Here, GLN is the invertible complex matrices. You all know that there's the polar decomposition, which says that such a matrix can be written as unitary times Hermitian positive definite. So if you mod out by the unitaries, you get the Hermitian positive definites. And so that's what this one is. By the way, these are terrible. The Cartan came up with these, but they have no really good meaning. Don't try to remember them. I don't. Sagu remembers them, but I don't. Let's see. These are the Grassmann manifolds, which are basically the hyperplanes in Rn or Cn or quaternion to the n. Okay, so these are the symmetric spaces, and you can color this list by random matrix theories. Okay, so if you go through the list, it turns out that the top left are the Hermite ensembles. You might know them as the Gaussian ensembles, the GOE, the GUE, the GSE. The joint densities are up there. You might recognize them with the Gaussian weight functions. Okay, the upper right one are the circular ensembles. The bottom left are the Laguerre ensembles. Those are the ones where you take the SVD of a rand n, or a Wishart matrix is sometimes what it's called. And these are Jacobi's. Okay. But the problem that bothered me is that you don't get all the Jacobi's, right? So in particular, you only get, when beta equals 2, for example, so here's your joint density for the Jacobi ensembles. When beta equals 2, you only get the ones where one or the other of these exponents is 0, right? Pretty sparse list. I mean, I wanted every one of these lattice points, but you only get these. Okay, so what good is a theory that leaves some of these biggies out, right? It just kind of bugged me. And so that's why I've sort of half colored the Jacobi. It's there, but not quite fully there. So where are they? What happened to them? Yes? I'm sorry, I can't hear you, and I'm sure neither can the audience.
Explain the color coding that made the same space in the upper left.
So these symmetric spaces are somehow associated with these random matrix ensembles.
Is it simple to say how they're related?
So yes, but then I'm going to say another word. You're going to keep this will continue for a little while. But there's a natural KAK decomposition that Cartense found. Actually, Cartense really didn't find it, but he sort of 90% found it, and people give him credit for giving it. So there's a KAK, which is basically a matrix factorization. And if you have the right measure on these symmetric spaces, in the compact case, it's the uniform measure, in the non-compact, it's the Gaussian measure on the tangent space, then the A's have these joint densities. Okay, so there's the sort of a little bit too quick answer to the question, but I'll say more. But their point is that there is an algorithm where you give me a symmetric space, and I can produce, I mean, a mental, not a mental algorithm. You give me a symmetric space, and these folks, executed this algorithm, so to speak, can produce a random matrix ensemble out of it. All right. So let me give you a little bit of a clue as to how we could. So I'm not finishing the story just yet, but I'll give you a little bit of a clue as to how we can get the rest of the Jacobi's, the ones that I was looking for. And for that, I'll say a little bit more about what to kind of sort of fill in the question that Rich just asked me. So let me take an example. Okay, so let's imagine we take, say, real n by s tall, skinny orthogonal matrices. Okay, so this X here could be thought of as simply a tall, skinny orthogonal matrix. S orthonormal columns in Rn is all that is. But I don't want this to represent X alone as a point. I want the equivalence class of all such X's that span the same column space. Okay, so that's called a point on the Grassmann manifold. Okay, and if you look at the KAK decomposition you won't find this in the right books, but if you kind of turn it on its head and look at it properly, you find out that Cartense KAK decomposition is a coordinate system on that manifold, where in effect, U and V have orthonormal columns. C and S are like the cosine and sine matrices in the CF decomposition, a diagonal of C's and a diagonal of S's that are positive, and C squared plus S squared equals 1, just like you'd expect. But this happens to be square. Okay, it kind of reflects the story. I don't know if you know the history of the CS decomposition, but the CS decomposition was discovered in the square case a couple of years before it was discovered for the general case, right? And it looked like the same thing happened in pure mathematics, where the Cartense decomposition did that first, and then later on, it can be generalized. So for those of you who may be familiar with the GSVD, the generalized singular value decomposition, maybe I should say a word or two about that. So when I started as a faculty member, nobody knew about the SVD except numerical linear algebra people. right? And then one by one, fields would discover it. Now everybody knows the SVD, even pure mathematicians who might have been the last, I'm not sure. But biologists and chemists discovered the SVD, economists one by one, and now everybody knows the SVD. Well, the GSVD, I think, is kind of where we were when I was a new faculty member, that only numerical linear algebra people know the GSVD. And maybe you'll start to see one by one, new fields discovering it. But essentially the GSVD is a coordinate system on a Grassmann manifold from a pure math point of view, but it doesn't have this restriction that Q equals S. And you just do that, and all of a sudden you get all the Jacobis. Okay, same manifold, different coordinate system. Okay, so we found some other surprises, and I promise I am going to go back and backfill some of the details, but I just want to get the main story out as best as I can figure out how to do that. So I think the hope was, Dyson's original hope, and the folks that followed him, that this would be a nice one-to-one situation where every classical random matrix theory would be associated with one symmetric space. Well, it turns out that it's not one-to-one, it's neither surjective nor injective. That's just the way the mathematics goes. It's not as pretty, but it is the way it is. So for example, I'd like to show you that on this slide, I'd like to show you that there's two manifolds, one real and one complex, that will lead to the same random matrix theory. Okay, and that random matrix theory that I'm going to point to is a beta equals 1 random matrix theory, often associated with reals. Okay, and so the two manifolds, this one's the easy one. You start with the real Grassmannian, which is that 8 rows, 2 columns, tall, skinny orthogonal matrix I mentioned before. This is not complicated. In fact, in Julia, you could just do this, or any, almost any computer language. You can actually start with Gaussians. You don't even have to orthogonalize because the GSVD will do it for you. So this would be the code you would type to generate matrices that have eigenvalues that, well, the generalized singular values actually that have that distribution essentially. Okay, or you can start with this manifold and do a rather funny factorization, one of the newer ones that wasn't out there. You could take any n by n unitary matrix and write it as an n by n orthogonal times a matrix that has cosines and I times sines in this arrangement, and then blocks of unitary matrices. Okay, and then you could look at the cosines and sines here, and this will have that same distribution. It's a complex manifold, but it has what looks like a real random matrix theory. So that's strange. So these two are, this is 2 to 1. Okay, and so it's not injective. And another case shows that it's not surjective. I guess we kind of already knew that it wasn't surjective because there are many ways to do the GSVD on the same manifold. But here's a particularly fun one because we're going the other way. We have a real manifold, but it turns out that you can get a complex looking random matrix theory. So you start with a real manifold, okay, and you do this matrix decomposition, and you end up with a beta equals 2, which we often associate with complex random matrices distribution. So the story is kind of interesting in crazy kind of ways. Okay, maybe I'll get back to this slide towards the end of the talk, but I just say a few things, kind of repeating. I may have said this. Oh, yes?
It's probably a stupid question.
I like stupid questions. I always ask them myself. Yes?
The last example, it's the eigenvalues of that central matrix.
It's not the eigenvalues per se, it's the parameters in that central matrix that matter. So just like with the SVD, I would never say it's the eigenvalues, it's the sigmas that, right, if you had, right, it's the cosines and sines play the role of an eigenvalue, right, or a singular value in that case. Those are essentially distributed in the same manner as, that's right. Yeah, there's a couple of differences, but yeah, yeah, this isn't like a block like the CS. This is a, yeah, and yeah, that's right. That's right. Yeah. Okay. So here's a geometric picture that tries to tell this. It's a bit of a tricky story. The non-compact and compact have some differences, but let me just mention that there are these manifolds. You look at the uniform measure when it's compact, and you look at the Gaussian measure on the tangent space when it's not compact. And Cartense theories follow these purple lines on the left. And we put in some examples so you could sort of recognize them. For example, the positive definite eigenvalue problem is on the left over here. The squared GSVD is here. If you can do these double coset representations, you get generalizations. Here you get the hyperbolic SVD and the generalized SVD. All right. So more about that in a moment. But we've also put, for example, the Jacobians of these here and so forth. Okay. More on that in just a bit. Okay. Back to the NLA problem. Which groups have structured SVDs? This is a table of Lie algebras over here, a notation that I prefer over Cartense notation. But all of these answer the question that was in the Lie algebra case that the Mackeys and Francois had asked. Okay, so now I'm going to backfill for whatever time I have and tell you all the definitions I might have told you to start. Okay, but we'll see how many I can get through. Right. First of all, let's talk about classical random matrix theory. Right. So I love the way that Hermite, Laguerre, and Jacobi are everywhere. The names, of course, go with the orthogonal polynomials, but it seems to me that Hermite, Laguerre, and Jacobi sort of are showing up all over mathematics, but not with their names. It's just associated with the situations. Okay, and so I like to think about Hermite, Laguerre, and Jacobi. And the way I like to think about it, and most of you would know this stuff, but it's fun to do it anyway, is I like to start with the 1-by-1 random matrices, the scalars, right? And if anybody walked into a basic probability class, there would be some distributions that would sort of be big stars, right? Really important ones, right? The standard normal, the chi-squared, and the beta distribution. And here are the probability densities, which of course are also the weight functions for Hermite, Laguerre, and Jacobi. Okay, when we get into random matrix theory, we graduate from scalars to matrices, right? Lots of good math goes from scalars to vectors to matrices. So we go to matrices, and we have these ensembles, the Hermite, Laguerre, Jacobi. I guess Arno didn't mention Laguerre and Jacobi explicitly in his list of 5 things that everyone should know. So we can sort of add that to the list, perhaps. Okay, so Hermite, as Arno mentioned, this one is you take a Gaussian and symmetrize it. Laguerre you can get by singular values or by forming G transpose G effectively, where you get the square. The Jacobi you get these Wishart matrices where the eigenvalues are on the unit interval, or you can do it with the GSVD. One thing to mention is the Dyson talked about these Gaussian ensembles in 1955, and I've seen lots of papers that say that random matrix theory started in 1950 something, thanks to Wigner, but that's just not true. The Laguerre and Jacobi go back to the 1920s and 30s, and it was sort of interesting that statisticians were interested in these two for very particular purposes. And they were very interested, of course, in the finite size matrices, where it seemed more likely that in the Gaussian ensembles, it was the infinite statistics that mattered more. And it took quite a lot of years for that kind of to get merged. But nonetheless, Hermite, Laguerre, Jacobi, classical random matrix ensembles. And in fact, if you look at books by Forrester and lots of other folks, the term classical random matrix ensemble, I think it's pretty well established, right? It's basically these 3 on the circular ensembles. We take real complex quaternions, and of course, these are essentially quantized in the classical cases. It doesn't have to be, but M1 and M2 or M and N should be positive integers or something, but that can be relaxed. Okay, so these are the classical random matrix ensembles, okay? And they're associated with 3 biggies in numerical linear algebra, right? The eigenvalue problem, the singular value decomposition, the generalized singular value decomposition, right? And so if you want to calculate these things, this might be about as good a way as any to draw draw points from these ensembles, right? To use the eigenvalues, the SVDs, and the GSVD. Numerical algebra, they tell you never form a transpose A, right? That's like considered a crime against humanity or something. Okay. Lie groups. Quick thing about Lie groups. So this is how I'd like to introduce Lie groups. It's not how you'll find it in your basic math course, but I like to start out with easy problems and then generalize. So here's two easy problems. If I ask you to solve g squared equals 1 for a real g, okay, so that's easy, right? There's your answer. And if I generalize that to the matrix case and said, can you solve g transpose g equals I for a real g, you would say, oh yes, those are the orthogonals. I know that. Okay. Well, one good way to think about the classical Lie groups is to think of that as a generalization of that simple problem, right? So given a matrix J and some notion of a transpose, which might be the ordinary transpose or the Hermitian transpose or some sort of quaternion transpose, solve this quadratic matrix equation, okay? And the solution gives you the classical Lie groups, right? So you go into a Lie group course, you might see tons and tons of definitions before you find that out, but this is how you get the classical Lie groups, okay? And so here are some of the symbols that you might see. The J's that people use, the identity gives you the orthogonals, the unitaries, and when beta is 4 is the symplectics. You can use the ordinary transpose instead of the conjugate transpose, and you've got two more Lie groups. You could take, instead of the identity, you can have a signature that's plus and minus, the indefinite unitaries, or you can sort of go this way on J and get the symplectics, right? And so these are the symbols that you would have seen in my chart on my first few slides. Okay, let me see, got a few more minutes. Okay, so let's get to the good stuff, the symmetric spaces. Make sure at least I cover that. All right, so what's a symmetric space? Okay. Well, if you go to the fancy books, there's a lot of definitions about geodesic reversals and vanishing covariant derivatives of curvature and so forth. The symmetric spaces are tricky. So I'm just you can look it up if you like. There's Wikipedia articles on it, but let me just tell you that these are spaces with lots of symmetries. Essentially, that you can transform the space and the curvature remains constant, which is sort of one of the. I like to think of it as like a sphere on steroids, right? Because it's like that symmetric. Okay, so these are the symmetric spaces, and they're usually, as you saw in the charts, they're Lie groups or a quotient space of Lie groups, and of course, you're already starting to see they connect matrix factorizations and they show up in random matrix theory. Okay. You saw this list, okay? And let me say a few words about Cartense decomposition. I pulled up some silly slides that I showed at a householder symposium 20 years ago. I'm right there in that, at the dinner. Seems like a long time ago. At the time, I started to read Helgason, which is really hard to read. It's not because the math is hard. It's because it's written in a way that's hard. Right? Don't confuse those two. A lot of people do. So Helgason's my colleague, and I've spoken to him, and he's told me that, well, he wrote this book because Cartan was hard to read. So, there's always a pecking order, I guess. Okay. So at the time, I understood, that there was a theory in there, but I didn't understand it as well as now. So I was wondering, where do matrix factorizations come from, like the SVD? And I'll just kind of like take you through a little bit of a story. As you all know, any matrix could be written as anti-symmetric plus symmetric. Okay, this is sort of the one example of the basic decomposition that leads to the KAK. You take the matrix exponential and you get the polar decomposition. Right, this is kind of a recipe that gets followed over and over again in Carten's work. Okay, and then you look for a maximal abelian group, and diagonal matrices form a very nice abelian group, right? And so you get the positive diagonals is a good choice. Those are what goes into the sigma. Okay, the Q that you got over here goes into the U and the V. Okay, so this is a subgroup of S, I should have said, right? So a subgroup of the positive definite matrices, that's abelian. right? So you always knew sigma as being a diagonal matrix, but Cartan knew that it's a maximum abelian subgroup of the positive definite matrices, right? And you put them all together and you get the SVD. Okay, and so this is what gets done over and over again. Okie dokes. All right, so to put this all together, what we needed was the generalized Cartan decomposition. This is a so-called double coset space where, in effect, instead of having a K on both sides, we have two different Ks. This goes back to Franz Jensen in 1978. And I looked it up, and it said that he was at MIT in 1978. So I started to ask around if anybody remembers him being there, but I haven't gotten a good answer yet. But these turn out to be the things that seem to be relevant for numerical linear algebra. They seem to be relevant for random matrix theory. Okay, I'm never going to get through this, so I think I'm going to skip this part. But just to quickly mention that a slide rule is an example of a symmetric space, right? And if you're interested, I'll tell you more during the break or something. Okay, and in some sense, positive definite matrices could almost be thought of as slide rules along the geodesic. You just change your measure as you move, as you slide the slide rule. There's a way of measuring things at different points, and that becomes your symmetry. Okay. If you look at the papers, we've written code that you can actually play with the various Lie groups. For example, if you want to play with the Lie algebra here, you can just construct these matrices and then take the matrix exponential. So I invite you to take a look if you're interested in these things. We tried our hardest to explain these things very clearly. Let's see. Oh, this is a fun one. How much time do I have? I probably used up my time, right? I've got 5 minutes. So one of the matrix factorizations that's kind of fun to think about is the hyperbolic SVD. So sometimes I've done this with I've got a picture of my dog and I've rotated him both. I don't have that here right now, but an ordinary rotation, you can just do this in space. A hyperbolic rotation, instead of things moving on circles, the points move on hyperbolas. And so here you can see an ellipse and a circle. Okay, you do a hyperbolic rotation, the ellipse becomes the circle, and the green and red points, you see the green and red points still follow the hyperbolas. Sigma is an ordinary dilation, okay, and this is an ordinary rotation. And you could see the SVD ellipse versus the HSVD ellipse all at the same point. Okay, it's fun to watch these things. Okay, so this is one of the factorizations, the hyperbolic SVD. Okay, I think, again, there's too much stuff, but you could take a look at the paper. We actually describe how essentially you can build these matrix factorizations, right? Again, I'm just gonna wave my hands and show you a few things. But you basically pick up a Lie group from this table that we have, okay, and then you look at another table and you pick up another Lie group, okay, and then you look for a function that's called an involution, like essentially you create something like a transpose, okay, and then you figure out what are the eigenspaces of this transpose. And so just to give you a simple example, if you were looking at the function that took x, a matrix x to minus x transpose, right? If you looked at symmetric matrices, if x was symmetric, then minus x transpose is minus x, right? And so that's in the -1 eigenspace. If you look at anti-symmetric matrices, minus x transpose is equal to x, and so that's in the +1 space. And so it decouples between those two spaces. So once you've got a kind of an involution like a transpose, you can separate matrices into these two spaces, and then you can exponentiate. And then again, I don't have time for the details, and please forgive me, but in effect, you can do this again, and you get this decomposition. Okay, so this is all in Cartan and Helgeson. Well, not this case, but it's Franz and Jensen, but it's hard to read. Okay, so let me kind of get to the summary. So in numerical linear algebra, I've been to many conferences where people like Charlie Van Loan and others would say, I'm always looking for a new matrix factorization. Right? It's always fun to find new matrix factorizations. And so we've produced a whole bunch of new matrix factorizations, all with sort of nice mathematical properties. Okay? Nice orthogonal type group properties, right? Not LU, but SVD-like things. Okay, we've sort of clarified the notion of the matrix factorizations that you would want in random matrix theory using these ideas. And let's see, we've, again, not enough time to talk about it, but I'd love to talk to anybody who's interested. Here, these factorizations lead to some new random matrix ensembles. So for example, you can get some non-classical ensembles. So the red dots here correspond to classical Jacobies. Okay, and you can get these purple Jacobies as well, and these green Jacobies. Okay, and so it's kind of crazy what you get from these symmetric space approaches. Okay, so there's new random matrix theories come from this. And finally, the completion of Dyson's symmetric space dream, where in the end, classical random matrix theories correspond to structure, they correspond to matrix factorizations, double coset spaces. We have some surprises. It's not neat and tidy. It's not bijective, it's not surjective, not injective. It's kind of a disappointment. I'd be sad, but it is the way that the math is structured. But it's okay. Okay, and this is my last slide. So, math is a great subject. We all know that. I remember when I was a postdoc and I went over to Jim Demmel and I said, "Did you know that this was connected to that in mathematics?" And I remember Jim said, "Oh, in math, everything's connected to everything," right? And of course, that very much is true. And of course, mathematical notation could be daunting. But I've always said that it's easy to make easy math look hard. It's hard to make hard math look easy, but it's worth it. So thanks very much.